In this slidecast, we'll talk about 2-3 trees. Now, a 2-3 tree consists of nodes that are either 2 nodes or 3 nodes. And a 2 node is the binary search tree node that you're familiar with. It has a data value and 2 child nodes. The left child has all data fields less than the node's data value, and the right subtree has values that are greater than the node's data value. So the 2 node is what you already are familiar with. What's new is a 3 node, and the 3 node has 2 data fields. Okay, the first data field is less than the second, and then there are 3 children. And the one child has data values that are less than the first. The next child, the middle child, has data values that are between the 2 data fields, and then the right child has data values that are greater than the second data field. And all the leaves of a 2-3 tree are at the lowest level. So here are pictures. Here is the 2 node. This is the node you're familiar with, and there's an expression here to represent what the values are in the subtree compared to the data value x that it's at the root of the 2 node. And here is a 3 node where we have 2 values and 3 children, kind of 3 subtrees. And the middle subtree has values that are between x and y. And the right subtree has values that are greater than y. And now here is a tree that has both 2 nodes and 3 nodes. So notice here's a 3 node, and it has its 3 children. Notice how the data values in the children, how they're related to the data values here in this 3 node. And then notice here's a 3 node that's at a leaf where the 3 children are all, the values are always null. Here is some pseudocode for how you would search a 2-3 tree. And it should seem very familiar to you as kind of the recursive way that we search a binary search tree. So here's some base cases. If the local root is null, then we return null because the item's not in the tree. If it's a 2 node, then this code here should be very familiar to you. If the item is equal to the data field, then we return that data field. That's the base case. Otherwise, we recursively search either the left or right subtree, depending on how the item that we're searching for is related to the data field, whether it's less than or greater than the data field. And then here's the 3 node, and it has 2 base cases. If the item is equal to data field data 1 or field data 2, then we found it. Otherwise, we have 3 choices. We have to recursively search one of the subtrees. And again, the choice depends on how the value we're searching for is related to the 2 data fields that are in the 3 node. For instance, if it's between the 2 values, then we would recursively search the middle subtree. Okay, so this is just the recursive search of a 2-3 tree. So here's a picture. Here's a 2-3 tree, and let's search for the item 13. We start at the root. Since 13 is greater than 7, we'll search the right subtree. That means we'll make a recursive call, and we'll search on the right subtree. Now this is a 3 node, so we compare 13 with the fields 11 and 15. And we can tell that 13 is in between them, so we will search the middle subtree. And now we find that 13 is the data field here, and so we found what we were searching for. Now, to insert an item into a 2-3 tree, the interesting thing about the 2-3 tree is it always stays balanced. And the reason for that is we build it from the bottom up, not the top down. So instead of hanging a new node onto a leaf, we insert the new node into a leaf. We always do that. And then when a leaf becomes too full, we'll handle it by pushing values up in the tree and possibly increasing the level of the tree by 1. All right, so here's a 2-3 tree with 3 values. And if we want to insert a 15, we'll handle this much like we saw earlier with inserting values into binary search trees. We'll compare that 15 is greater than 7. Once we look at the right subtree, because this is a 2 node, we'll just place the 15 right in this node. So now we'll have 2 data fields and we're finished. And the tree still stays balanced. Now if we were to insert a 17, we'll again go to the right subtree. And what we will do, we'll say we'll virtually insert it into this node. Maybe it just temporarily we'll insert it, so now we have 3 values. But in our 2-3 tree, the nodes can only have 1 or 2 values. So what we'll do is we'll take the middle value and we'll propagate it up to the parent in this fashion. So now we have a 3 node at the root of the tree with 3 subtrees. Okay, let me back up and show the before. Here's the before case where we have 11, 15, and 17. So what we're going to do is take the 15 and move it up. And since things to the right are greater than 15 and things to the left are between 7 and 15, then that will naturally help us form this 3 node with 3 children. Now let's insert the values 5, 10, and 20, and they'll each go into the children. So now all of the children become 3 nodes. And now we'll insert the value 13. Since 13 is between 7 and 15, we'll add it to, kind of virtually to this child. So now this child has 3 values, so we need to propagate the middle value to the parent. When we put it to the parent, we'll temporarily form another node, again with 3 values and 4 children. And what we'll want to do is kind of the same approach. We'll take the 11 and promote it to the parent, so we'll create a new root. And then we have to split the remaining values into 2 nodes in that fashion. All right, here is the algorithm for inserting into a 2-3 tree. So this is the case. It's going to be a recursive algorithm. If the root is null, then we create a new 2 node that contains the item. If the item is in the local root, then we return false. So we don't have duplicates in our 2-3 trees. Otherwise, if the local root is a leaf, if it's a 2 node, then we expand the 2 node into a 3 node, and we insert the item into its correct place so that the data is ordered. Otherwise, we split the 3 node, creating 2 nodes, and pass the new parent and the right child back up the recursion chain. Now, if the item is less than the smaller item in the local root, then we recursively insert into the left child. If the local root is a 2 node, then we recursively search into the right child. Otherwise, if the item is less than the larger item, then we would recursively insert into the middle. Otherwise, recursively insert into the right child. And if a new parent was passed up from the previous level of recursion, then if the new parent will be the tree root, then we create a 2 node whose data item is the passed up parent, and the left child is the old root, and the right child is the passed up child. And this 2 node becomes the new root. This is what happens when the end result is a tree whose height is increased by 1. Otherwise, we recursively insert the new parent at the local root. Here's another example. Let's create a 2-3 tree using the words from the sentence we've used during the semester. The quick brown fox jumps over the lazy dog. So we'll start with the, and we'll have a node with 1 value. When we get quick, we'll get a 3 node. Next we add brown. We'll temporarily create 3 values, and then we've got to promote brown to the root. Then we add fox. Then we add jumps, and jumps is the middle value here in temporarily, so we're going to promote jumps to the parent. And now we're done. So we have a 3 node at the root and 2 nodes as the children. Then we add over. We add the. So now we've got a node that's too full. We've got to take quick and promote it to the parent. And then we temporarily have another node that's too large. What happens here? We take the middle jumps, promote that to the new root, and brown and quick become children. Then we add lazy, dog. And now we're finished. All right. Now let's analyze a 2-3 tree and compare it with a balanced binary tree. So 2-3 trees do not require the rotations that we had for AVL and red-black trees. So in that sense, their implementation is easier, maybe not as complicated. The number of items that a 2-3 tree of height h can hold is between 2 to the h minus 1, a tree with all 2 nodes, and 3 to the h minus 1, which is a tree of all 3 nodes. So the height of the tree is somewhere between log to the base 3 of n and log to the base 2 of n. So the search time is a log n. Logarithms are all related by a constant factor, and constant factors are ignored in the big O notation. Now removing from a 2-3 tree is kind of the reverse of the insertion process. So if an item is to be removed as a leaf with 2 items and we delete it, if it's not a leaf, then remove it by swapping it with its in-order predecessor in a leaf node and deleting it from the leaf node. And then if removing a node from a leaf causes the leaf to become empty, then the items from the sibling and the parent need to be redistributed, or the leaf can be merged with its parent and sibling nodes. So let's look at some examples. Here's a 2-3 tree. We're going to remove 13. So by removing 13, a node becomes empty. So we merge 15 with a remaining child. So we take 15 and place it here. Now this node is too full, so we need to split it and move 17 to the parent. And now we're done. So let's remove 11. So if 11 is removed, because 11 is not in a leaf, we replace it with its leaf predecessor, which is the value 9. Now because 11 is not in a leaf, we replace it with its leaf predecessor. And then the left leaf is now empty, so we have to merge the parent into its right child. So the 9 goes in with the 15, and now we're finished. Let's remove 1. So in this case, we have to merge the parent with its right child. And then we repeat on the next level. So we merge the parent 7 with its right child, 17. And we bring up the 3, 5, and we're done. And that brings us to the end of this slidecast.